Hi everyone. Hello and welcome. Today we're talking about quadratic equations in section 3.3, section 3.4, section 3.5. So previously we introduced a lot of different ways we could represent a quadratic equation. We have standard form, just some ax squared plus bx plus c. We also have factored form, so a times the quantity x minus r times the quantity x minus s. And we have vertex form, a times the quantity x minus h squared plus k. Note in all cases, this a is the same. Whatever is our leading coefficient, it's going to be carried through whether it's 1 or some other number. How do we go between these? Well, it turns out going from standard form to factored form, you just factor, right? And going from standard form to vertex form, well, you have to complete the square. Going the other direction is really easy. Just expand and you can get back to standard form. Okay, so now we're going to go over that more carefully. That's the idea with section 3.3. So think about how to convert from one form to the others. To go from standard form to factored form, easy enough, just factor. We're using the distributive law in reverse. So no further explanation until we get to an example. The more interesting one is going to vertex form. So here we need to recognize a quadratic expression that's a perfect square. So what's a perfect square? We have a perfect square trinomial where whatever is this term squared and whatever is this term squared, if you can find the constituent factors, multiply them together, and then multiply by 2, you get the middle term. Here's an example. Y equals x squared plus 6x plus 9. Think about the prime factorization. So the prime factorization of 6 is 2 times 3. Prime factorization of 9 is 3 squared. Oh, 2 times 3, 3 squared, right? So we recognize the factor here, 3, multiplied by 2, gives us our middle term. That's the property the perfect square trinomial has. Well, this being the case, we can exploit this fact and we can write the factorization as x plus 3 squared. Think about why that's the case. Let's expand this. Let's FOIL it. What are we going to get? We're going to get x squared at one end. We're going to get 3 squared, 9 at the other end. What about in the middle? In the middle, we're going to get you're going to get 3x plus 3x, 6x. Okay. Suppose we have something that's close to a perfect square, not exactly. We have an 8 here. Well, we can manufacture a perfect square. How do we do this? Well, suppose we add 1 to both sides. If we do that, that'll preserve this equality, and it'll convert this 8 to this 9. We're just going to ignore the left-hand side for the time being, and we're going to write the right-hand side as the perfect square we know it is. And then we'll solve for y, and this is vertex form. Now we have our h and we have our k, and this process is called completing the square. Just adding a constant to both sides such that the right-hand side becomes a perfect square. So that's super clever. I think that's kind of cool. All right, so let's try that here. So we have x squared minus 4x minus 12. It's in standard form. A is 1, b is minus 4, and c is minus 12. Now let's put it into factored form. Well, to do that, we just have to factor and then put it in vertex form. We have to complete the square. 12 is not a square. Okay, so stop the video. Go ahead and do that. All right, so it's in standard form. We want to factor this. I mean, maybe just staring at this, you know the factorization is x minus 6 times the quantity x minus 6 times the quantity x plus 2. Just for the sake of explaining factoring by grouping, let's do that. Factoring by grouping amounts to finding the product a times c. So in this case, 1 times minus 12 is minus 12. And then finding two numbers, m and n, such that they multiply to give us minus 12 and they add to give us the b term, minus 4. Well, 6 and 2, of course, minus 6 and 2 do that. Minus 6 times 2 is minus 12. Minus 6 plus 2 is minus 4. So I'm going to replace this minus 4 with this minus 6 plus 2. Minus 6x plus 2x. We add this together, collect like terms, you're back to here. Why do I do this? Well, this is cool because this will demonstrate factoring by grouping, which is super useful if this is not 1. Okay. So now what I'm going to do, I'm going to factor out an x, and I'm going to factor out a 2. When I do that, I'm left with an x minus 6 and an x minus 6, and this becomes a common factor. So now I'm going to take out the common factor of the quantity x minus 6, and I'm left with an x plus 2, put parentheses around that, and multiply it by the common factor I just took out. Notice this is just the distributive property in reverse. All right, suppose we expand this by the distributive property. We distribute the quantity x minus 6 to the x and to the 2 across this sum. Here's what we get. And then continue to expand, collect like terms, and we get to there. All right, well, anyhow, this is factored form. And this also gives us the zeros of the polynomial, which is cool. All right, so this is factoring by grouping. It's quite powerful, especially for difficult factorizations. That's what I was saying before. Super useful if this is not 1. So this is an easy one. You probably don't need to do factoring by grouping here, but I think seeing this is helpful because it's sort of an archetype problem. It shows us the method that we can now apply in more complicated situations. All right, so now let's put this thing in vertex form. What's going to be our perfect square? Well, x squared, that's already square. We got to build a square here, but we want to do that cleverly because we know the middle term, which we're not going to be able to do anything to, right? The middle term we're not going to be able to affect, or we're going to try not to affect, is going to be minus 4x. So that's like 2 times 2. Oh, okay, well 2 squared is a square, so that's 4. How can I build a 4 here? Well, I can build a 4 by adding a positive 16 to both sides. So that's what I've done. So I've got y plus 16 is equal to x squared minus 4x plus 4. Right, minus 12 plus 16 is 4. Cool, because this right here is a perfect square. Right, think about expanding this. X times x squared, minus 2 times minus 2, 4. Minus 2 times x plus minus 2 times x, minus 4x. All right, so we move this to the other side. We actually have y is equal to the quantity x minus 2 squared plus minus negative 16. Why did I do this? Well, just to preserve the vertex form from before. We see h is equal to 2, and then k is equal to minus 16. All right, so hopefully that's what you've got. Basically, we're just being clever to be able to make this thing a perfect square trinomial so that we can write it in this form. All right, here's another example. So suppose we want to find the maximum or minimum value of a quadratic function. We use completing the square to express the function in vertex form. All right, suppose we have a street vendor. It finds if it charges P dollars for a blanket, its revenue from blanket sales is just given by this function, price times quantity. Price times 300 minus 10p. You don't care about this right here, but this is actually a demand curve. All right, so what price should it charge to maximize revenue? To figure this out, we can complete the square. All right, so go ahead and do that. Do the completing the square exercise, and then interpret your equation so that we can find the maximal revenue maximizing price. Okay, so let's go ahead and expand this. We have 300p minus 10p squared. I know if you know calculus, you're really tempted to just take the derivative and write this as 300 minus 20p and then divide through by 20 to find your p. Let's not do that. Let's do this algebraically. The coefficient of p squared is minus 10, so we know the quadratic opens down. The vertex is our maximum. All right, let's find the vertex. That's why we want to use vertex form, because we know when we find that vertex, that'll give us our maximum. And we know our coordinates on the horizontal are going to be, and the vertical are going to give us the right interpretation to find the revenue maximizing revenue level and the revenue maximizing price. Okay. So here we begin. This looks scary. Let's unpack this slowly. Here's our revenue expression, 300p minus 10p squared. Okay. Well, the first thing I want to do is I want to get this thing looking in the form that we had before, right? So when we looked at this expression here, we had our a term was 1. All right, so I'm going to divide through so I can build that here. Here my a term is not 1, my a term is minus 10. So I'm going to divide by negative 10. And when I do that, I'm going to get positive p squared minus 30p. All right, this is looking a little bit better. Now I'm going to stare at this and I'm going to say, okay, I got to build a perfect square. Well, this is 2 times something, and that something is 15. 2 times 15. Oh, if I just write 15 squared, then I'll have my perfect square trinomial. So let's do that. Let's just add a positive 15 squared to both sides. So I did that. That doesn't change the balance of the equation. I could have added positive 1,000,000 to both sides, positive 10 to the 6th. Doesn't matter. Could subtract 15 squared from both sides, but that's not going to do exactly what we want it to do. It's got to be plus 15 squared, because this here is a perfect square trinomial. Namely, it's p minus 15, that quantity squared. All right, now I'm going to unpack this, and I'm going to solve this for r, basically. So I'm going to add that 15 squared to this side, or subtract this 15 squared from both sides, and then I'm going to multiply through by a negative 10 that switches this sign, right? Negative 10 times negative 15 squared is positive 10 times 15 squared. Oh, 15 squared is 225 times 10 is 2250, right? Okay. All right, so our vertex is the point 15, comma 2250. I know this looks like I wrote 152,250 completely wrong. That's not what this is. I should have written this better. Apologize for that. This is supposed to be parentheses 15, comma 2,250 parentheses. Right, so the revenue maximizing price is 15. The maximum revenue is 2250. We see that from interpreting this thing, right? Think about the algebraic structure. Where is this the biggest? Where is R the biggest? Where is revenue the biggest? Well, this is negative. Doesn't matter what this is, this thing's going to turn out negative, right? Because even if this term inside here is negative, it gets squared. So whatever is going to be, it doesn't matter what our price is going to be, this thing gets squared and then multiplied by negative 10. So this left-hand sum is going to be reducing whatever is the revenue down from 2250. The only way we can make that not happen is if this whole thing is 0. So let's set p equal to 15. That makes this 0 times 10 is 0. So then revenue is 2250. All right, so the revenue maximizing price is exactly 15 because that's what makes this whole thing turn to 0 and drop out. And then revenue is maximized at the level of 2250. All right, I think that's kind of neat. And here's the picture. Right, we found the vertex. We found the point 15, 2250. Revenue is the max revenue is 2250. The revenue maximizing price is 15. For prices between 0 and 15, revenue is increasing as price rises, and then beyond 15, revenue is falling as price rises, but revenue is still positive all the way down to a price of 30, in which case revenue would become negative, but the firm wouldn't do that. The vendor wouldn't sell for negative revenue. Okay, cool. So section 3.4, so thinking about quadratic equations. A quadratic equation is one that can be put in the standard form, ax squared plus bx plus c is equal to 0. So in other words, you have some expression, you have some thing that's not 0, move it to the other side, then we have standard form. All right, so what we're going to do is think about some of the approaches to solving equations of this form. So solve quadratic equations by factoring, by perfect squares, by completing the square, and then the quadratic formula. All right, so the first thing I'll do is, for solving by factoring, this rests on the zero factor principle. This is what I call the zero product property. Basically, it's the idea that if you have the product A times B, and if that's equal to 0, then either A is 0 or B is 0. Or, if you have the product A times B, and you can turn one of those A's or B's into 0, or both, the whole thing turns into 0. So here's, in our blanket example, P times the quantity 300 minus 10P is equal to 0. If we pick A to make this 0, oh, well, that's A is just P's. Let's just make P equal to 0, then the whole thing 0. Or if we choose P cleverly, that makes this B term 0. We know the solutions here are going to be P is equal to 0 and P is equal to 30. And that's what makes this whole thing equal to 0. What's this representing? This is representing revenue. That's this. Oh, that's what we found. Revenue is 0 when P is 0 or when P is 30. That's what this is saying. When we can easily factor the quadratic equation, we use this property to find the solutions, to find the zeros. All right. The other thing, factoring by perfect squares. In general, if we can put a quadratic equation in this form, x minus h squared equals c, with constants h, c, and some value positive, we can solve it by taking square roots of both sides. All right, so if I have a perfect square, what do? Take a square root, and then I'm going to have x minus h, which I can add a positive h to both sides and solve for x. So let's think about doing that here. Suppose we have x squared minus 49 is equal to 0. 2 times the quantity p plus 3 squared minus 4 is equal to 0. And 9 times the quantity y plus 1 squared plus 36 is equal to 0. So solve the quadratic equation by taking the square roots of both sides, if possible. So stop the video, go ahead and do this. All right, now coming back, hey, let's move this 49 to the other side, then take the square root. So we know the solution is x is equal to plus or minus 7. Why plus or minus 7? Well, 49, square root of 49 has there's two possible roots. Why? Why? Because what the equation we're trying to solve is x squared is equal to 49. There's two ways that can happen. We can either have 7 squared or we can have negative 7 squared. And since we don't know which one, we have to remain agnostic. And so we're going to write this as x is equal to plus or minus 7 because both of these are solutions to this equation. Okay. How about this one? Let's move the 4 to the other side. Divide through by 2. We have p squared plus 2 squared is equal to 2. Oh, let's take the square root of both sides. And forget about this 2 right here. This 2 that I've highlighted, that ought not be there. Well, actually, what do I need? I need parentheses. So there ought to be parentheses around this p plus 2. Okay, that evaporates and we get p plus 2 is equal to the square root of 2. And it'll subtract off of 2. So I get p is equal to the square root of 2 minus 2. Cool. Now this last one. Let's move 36 to the other side. Oh, 9 times y plus the quantity y plus 1 squared is equal to minus 36. Looks good over here. Here's 3 squared. This is squared. Oh, it looks terrible over here. Square root of 36 is not a real number. It requires an imaginary number. So this equation has no real solutions, and we're not going to worry about imaginary or complex numbers in this class. Okay, so yeah, so you get something like this. We say there's no solution. Okay, so next thing to do, let's solve quadratic equations by completing the square. So previously we saw how to find the vertex of a parabola by completing the square. Now let's just see if we can use this method to solve equations. So suppose we have x squared plus 10x plus 23, or we have 3x squared plus 6x minus 2 is equal to 0. So stop the video, go ahead and solve these. Thing you might think about is, remember, you want to think of the prime factorization here. 2 times 5. Oh, 5 squared is a perfect square. Can we make that over here? And then over here, 2 times, think about how we can do that there as well. Okay. All right, so here's the first one. You might recognize the left-hand side is not a perfect square. We need something in this form. For the x terms to match, we need what? P is equal to 5, and p squared is 25, so we can add 2 to both sides. If we add 2 to both sides, we'll get 25 here. And that's cool, that works out. So we'll have 4 over here, we have a perfect square over here, so we'll get, we can write we build a perfect square on the right-hand side, which is previously our left-hand side, without altering the equalities. We have x plus 5, that quantity squared is equal to 4. We can solve the equation. Let's take the square root of both sides. And then solving, we have x is equal to minus 3. All right, awesome. And this last one, well, let's first get rid of this a term, right? I want this a to be 1, so what can I do? I can multiply through by 1/3. Notice I multiplied this side, 1/3 times 0. Why did I do that? Well, this is to reinforce that if I'm going to multiply through by 1/3, I got to do the same thing to both sides. Real convenient over here because this just drops out, that's just 0. What happens over here? Well, I get 1/3 times this stuff plus 1/3 times this stuff plus 1/3 times this. And I should actually have equals 0, but I skipped that. Now I'm going to simplify down. I have x squared plus 2x minus 2/3, right? Minus 2/3 equals 0. Or I have x squared plus 2x is equal to 2/3. We still have to complete the square. So think about how that's got to work. Look on the left-hand side. I need to build a square out of this. Do you know what it's going to be? Well, here it is. The coefficient is 2. Half of this is 1. So we add 1 squared equals 1 to both sides. And now, sure enough, look at this. X plus 1 squared. Sure, x squared is x. 1 squared is 1. X times 1 plus 1 times x is 2x. Cool. So this is legitimate. Over here, I can think of 2/3 plus 1 as 2/3 plus 3/3 or 5/3. Take a square root of both sides. I'll have x plus 1 plus or minus the square root of 5/3 or negative 1 plus or minus square root of 5/3. Cool. And the last thing, quadratic formula. So you want to memorize the quadratic formula. Why? Because it comes up where you'd least expect it. So comes up in some in the economics classes that I teach. It comes up in the sciences. Comes up in a lot of different places. It's good to just memorize it. It's pretty low cost, right? X is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. I mean, that looks horrible at first, but once you start thinking about it, it's really not that bad. All right, so the text gives a nice derivation of where this thing comes from. Let's not bother with that, but it's worth reading through. It really is. It's kind of cool. All right, the quadratic formula is going to give us x values, solutions to this equation. This is useful if we're not able to factor something, or if it's prohibitively costly to factor. So use the quadratic equation to solve something like this, and then use the quadratic equation to solve something like this. So solve this first one, and then solve the second one using the quadratic equation, right? So here's A, here's B, here's C. Right, what's the quadratic equation? Minus b plus or minus the square root of b squared minus 4ac divided by 2a. All right, so stop the video, go ahead and do that. All right, here's the first. We're just going to make some substitutions, right? So minus b is minus minus 3 plus or minus b squared minus 4ac. Cool, divided by 2a. Don't forget that divided by 2a. Well, we get a 9. We get a plus 64, right? 32 times 2. This becomes 73. 3 plus or minus square root of 73 divided by 4. At this point, we can kind of break this up. We can write this as x is equal to 3/4, right? 3/4 plus or minus square root of 73 divided by 4. Sometimes there's something we can do to reduce this fraction. That's not super necessary in all cases, right? It's okay to have the radical in the numerator. If we had the radical in the denominator, we've done something wrong. But if you have a radical in the denominator, you've got to fix it, right? Then you're going to want to rationalize the expression, but we don't have to do that here because it's in the numerator and 73 is prime. So, all right. Here's the other one. Use the quadratic equation to solve n squared minus 100n plus 250, 2,500. So here we're just substituting minus b, so minus 100 plus or minus 100 squared minus 4 times 1 times 2,500. So we get 10,000 minus 10,000. Oh, that's cool. This is just 0, right? So we get x is equal to 100 plus or minus 0 divided by 2. Or x is equal to 50 plus or minus 0, or x is equal to 50. What on earth happened? Well, square root of 0 is 0. So there's just one solution. Think about what this looks like geometrically, right? Think about what the graph looks like. I won't spoil it. Use your graphing calculator or draw this out. Plot some points. Figure out what we just found. It's cool. Okay, so here we're going to introduce something more generally. The discriminant. The discriminant is the area under the is the term under the radical, and it gives us clues as to the solutions. So if we just have the quadratic equation and we look to find b squared minus 4ac, we can calculate, is this discriminant positive? If so, there's two distinct solutions. Is it 0, like it just was? Then there's one solution. Or is it negative? And then there's no real solution. So this can give us some clues, and that's useful. Okay. All right, the last thing. Let's think about some hidden quadratics. So let's find some quadratics in places we'd least expect them. They're hidden. All right, so suppose each blanket costs $5 to make. This is going to allow us to combine revenue and cost. That gives us profits. Profit is just revenue minus costs. We can write profits a variety of ways. So very simply, revenue is price times quantity. Cost is cost times quantity. So very often we write profit as just PQ minus CQ. Or you can write it as price minus cost times quantity. The quantity P minus C times Q, which is the factored form. Okay, so if neither of those made sense, don't worry about it. You won't hear that again unless you take Econ 101, and then it'll make a lot of sense because we'll talk about it a ton. Okay, so here we want to do is write an expression for the cost of making the blankets. We'll write an expression for the profit, revenue minus the cost, and then find out which values of P is the profit positive. And then interpret your answer in practical terms. All right, so pause the video, go ahead and do this. Or call the blanket example. Write the expression for the cost of blankets. Well, it costs $5 to make. What's the quantity? Remember I said this is the demand curve. Q is equal to 300 minus 10p. Right? Revenue is price times this amount. This right here is going to give us our number of blankets. So cost is just 5 times this stuff. Right? All right. Write an expression for profits, revenue minus cost. Well, this is revenue. We have our cost, right? So profit is revenue minus cost. So revenue is this, cost is this. So profit is going to be price times quantity minus cost times quantity. Alternatively, here's quantity. We could factor this out. So we could write this as P minus 5 times the quantity 300 minus 10p. But here we go. This is an expression for profit. All right. So for what values of P is the profit positive? The factored form is the most useful way to answer this. You'll see why immediately. Let's go to this. Let's factor, as I suggested, let's factor out this quantity, 300 minus 10p, and we'll get P minus 5 times the quantity 300 minus 10p. Look at this. This thing is P minus 5. This is positive for prices bigger than 5. This right here we already found was positive this is 0 when price is equal to 30, and then for prices bigger than 30 it'll be negative, right? So what does this tell us? If we factor this down further, you get a better sense. Take out 10, we have our real factorization would be quantity P minus 5 times 10 times the quantity 30 minus P. Why? Well, that's because this stuff right here is just this. Anyway, what this tells us is that, so here's that written nicely. Price is bigger than 30. Profit is this, so we get positive times positive, or positive times negative equals negative. How do we know? Price is bigger than 30. Well, when price is bigger than 5, this is positive. When price is bigger than 30, this is negative. So we get positive times negative is negative. Price is between 5 and 30, we get positive times positive, so it's positive. And that's what we want. This is actually, I mean, we're done here. But suppose we explore further. Suppose price is smaller than 5. This is negative times positive, so it's negative. In order for profit to be positive, we require the price is above 5, below 30. That's natural. So that's our restriction on price to have positive profits. Let's interpret the thing in practical terms. What does it mean that the price is between 5 and 30? Well, price has to be bigger than 5 because we have cost of 5. So if price is below 5, we're losing money in every unit that's sold. Right, so price has to be bigger than 5. What if price is bigger than 30? Well, if price is bigger than 30, then the price is too high. The quantity demanded at that price is going to be too low. People just don't want your blanket for $30. So the price has to be less than 30. All right, so these last things, let's solve using the zero product property, zero factor principle. So let's solve 2x cubed minus 5x squared equals 3x, and then a over a minus 1 over equal to 4 over a, and then solve x squared minus 1 over x plus 3 equals x divided by x minus, or x plus 3, a divided by x plus 3. Can't talk. Okay, so all right, we want to use this using the zero property, zero factor principle. Whenever you hear that, we know we want to factor something. Let's move this to the other side. Let's factor out an x. So here I've done that. See? Move this 3x to the other side, and then factor out an x. Cool. Alternatively, you could just factor out an x immediately on this side, and then move this over, and then factor out the x. Let's just do it this way. There we go. All right. We need two numbers that multiply to minus x but add to give us minus 5, right? So the product a times c is 2 times minus 3 is minus 6. We want to be able to add to get minus 5. That's going to be minus 6 and 1, right? So minus 6 times 1 is minus 6, and then minus 6 plus 1 is minus 5. Awesome. So I actually should have more parentheses. Sorry about that. But anyhow, we've done it correctly here. Let's group together the 2x squared plus x. Let's group together the 2x squared, this should be 2x squared plus, 2x squared plus 1. And then minus 6x minus 3. So I'll fix this for the slides on Canvas, so don't worry about that. But this is actually what it looks like. We're going to factor out an x. We take out an x, we get 2x, x times the quantity 2x plus 1 plus minus 3, 2x plus 1. Why did I take out the minus 3? Well, I want to be able to turn this term into a 2x plus 1, which I can then factor out. So I get x times the quantity x minus 3 times the quantity 2x plus 1. That tells me this is 0 when x is 0, x is 3, or x is plus or x is minus 1/2. And you can plug these back in respectively to see that that makes this product 0. So there we've solved it. Found the zeros of this quadratic. All right, so here's another one. How do we solve this? Let's just multiply through by a times the quantity a minus 1. Why? Well, here's one denominator, here's the other denominator. Their product has to be the common denominator. So let's multiply this by a over a. Let's multiply this by a minus 1 over a minus 1. That'll work. Alternatively, if I just multiply everything by a times the product of a and quantity a minus 1, see what happens. Well, these a minus 1's cancel. I'm left with a squared. These a's cancel. I'm left with 4 times the quantity a minus 1. Isn't that slick? I think that's cool. We can expand this right here, move to the other side, and then factor. Right? So when we do that, we'll get 4a minus 4. Move to the other side, we'll get a squared minus 4a plus 4, and then factoring is easy. Right? So we need 2, or we need 2 numbers that multiply to give us 4 and add to give us minus 4. Minus 2 and minus 2, right? Minus 2 times minus 2 is 4. Minus 2a plus minus 2a is minus 4a. Okay. All right, so I actually don't want this to be a minus 2 equal to 0. What do I want there? Sorry about that. I'll fix this. What does this have to be? That's got to be a squared is equal to 0. And then we'll take the square root of both sides, and then we'll have a minus 2 is equal to 0. And then we'll solve and get a2. So what did I do? I skipped some steps. It's not mathematically wrong. If maybe you see what happened. I mean, one way to justify this is let's just divide both sides by the quantity x over 2, or a over 2, and that'll do it, because this is a 0 over here. But I should have written that out a little bit more explicitly. All right, and then let's just check to make sure that here's our solution. Let's just check to make sure the factor we multiplied through is not itself equal to 0. So let's plug in 2 here. Sure enough, it checks out. That's just checking. Remember, we need the denominator not to be equal to 0 at any point, otherwise the fraction's undefined. Okay, and then the last one. Left-hand side and right-hand side have the same denominator. You could just multiply through by x plus 3, and then we just have numerators. If you do that, you have x squared minus 1 equals 8. Or we have x squared equals 9. Take the square root of both sides. We have x is equal to plus or minus 3. Okay, now here's our 0 restriction, 0 denominator restriction. Only x minus 3 is a valid solution. You're wrong if you say x is equal to minus 3 is a solution. Why? Well, put in x is equal to minus 3 there, and this becomes 0, and then our denominator is undefined. So we restrict our domain to exclude x equal minus 3. Okay, cool. Let me know if you have questions.